We present a computational approach for planning the assembly sequence of bespoke frame structures. A bespoke frame structure is a collection of bars that are joined together to form a 3D shape. An interesting question is how to find a good assembly sequence for building this structure. With a suboptimal sequence, intermediate subassemblies can have substantial deformations due to self-weight. We simulate their structural deformations using the finite element method, which is visualized by plotting the compliance energy over the number of installed bars. This sequence planning problem has an enormous search space, in which many sequences have large structural deformations during assembly. A popular approach that uses an assembly by disassembly search algorithm still generates a sequence that has substantial deformation. Our approach can efficiently allow us to obtain a sequence with greatly reduced deformation. Here is one assembly sequence of a 12-bar tower model. Each step of the sequence corresponds to a substructure. If we only consider the sixth step of a sequence, our goal is finding the stiffest 6-bar substructure. Our key insight is that we can formulate this problem using topology optimization, which minimizes structural compliance with a material budget of 6 bars. We can solve this topology optimization using a mixed integer solver. Then, a simple idea for solving our sequence planning problem is first to find the stiffest 1 bar, 2 bars, until 12 bars subassembly. We then connect these subassemblies to form a sequence. However, this sequence is not temporal coherent. Bars that are in the previous steps can disappear in the following steps. To address this problem, we propose a new temporal coherent topology optimization. Our formulation minimizes the structural deformations of all intermediate assembly states with coherency constraints. Here is a solution computed by our method. Our method naturally extends to multi-bar at a time assembly sequences, as we can freely choose the number of bars which need to be installed between 2 subassemblies. We can use this strategy to build this complex robot structure. For models with many bars, using our formulation requires us to solve a large mixed integer optimization problem that is costly in time. We propose a landmark method, which first finds a given number of coherent landmarks with minimum structural deformation. Then, by enforcing our assembly sequence to go through these landmarks, we can divide the whole sequence planning problem into several sub-problems with a smaller number of non-installed bars. We can solve each of the sub-problems individually using either our temporal coherent topology optimization, or a classic search-based method like greedy search. Here is the assembly sequence generated by our landmark method. Our sequence can reduce 67% of the compliance compared to a sequence generated by a classic greedy-based approach. Here is another assembly sequence for building this truss structure, which consists of more than 200 bars with different lengths and thicknesses. As we've seen, our method naturally supports assembling single bar and multiple bars at a time. We can further reduce structural deformations by adding a fixed number of supporting poles in optimal locations. Our method supports static scaffolding that are not removable until the end of the assembly, or make use of dynamic holding, which allows for dynamic relocation of a fixed number of static supports. For more details, please refer to the paper. Our method can compute the assembly sequence of building this frustum model by installing at most 6 bars at a time. By adding static scaffolds, we can reduce 98% of the compliance in assembling this arch model compared to the sequence without scaffolding. Our framework also allows reusing support during assembly, which helps reduce 96% of the compliance compared to the sequence without scaffolding. Thank you very much for your attention.